This is a physics explainer. We will show experiment evidence and sources, not mystical claims. Right now, before you hear another word, place your hand flat on the desk in front of you. Feel the solid surface, the resistance, the texture, because what you're about to learn will make that ordinary sensation feel genuinely strange, and every claim we make will be traceable to peer-reviewed physics. Here is the question that drove some of the 20th century's sharpest minds to the edge of philosophy. Does measuring a quantum system change it? Not metaphorically, physically. The answer, confirmed repeatedly in laboratories since 1909, is yes, and the mechanism is called the observer effect. Let's be precise about what that means, because popular science has wrapped this concept in so much mystical fog that the actual experiment, which is far more astonishing than the myths, gets buried. The observer effect is not about human consciousness. It is not about intention. It is about physical interaction between a measuring apparatus and a quantum system, a detector, a photon, a magnetic field. These are the observers physics talks about. Practical exercise 1. Pause for 15 seconds. Write down, on paper or in your notes app, your current intuitive guess. Do you think the act of looking at something changes it? Write yes or no, and one sentence explaining why. We'll return to your answer. Now, the double-slit experiment. Fire a stream of electrons, single electrons, one at a time, at a barrier with 2 narrow slits, and collect them on a detector screen behind it. When you don't measure which slit each electron passes through, the electrons build up an interference pattern on the screen, alternating light and dark bands, the unmistakable fingerprint of a wave. The electron, described by its wave function, passes through both slits simultaneously and interferes with itself. This is not interpretation. This is the raw data, reproducible in any quantum optics lab. Now place a detector at one of the slits, a device that registers which path the electron took. The interference pattern vanishes. Gone. In its place, 2 clumps, exactly what you'd expect if you were firing tiny bullets, not waves. The electron behaved as a particle the moment its path was measured. What changed? Not the electron's knowledge that someone was watching. What changed was physical. The measuring device exchanged energy or momentum with the electron, an interaction called decoherence, which collapsed the electron's spread-out quantum state into a localized one. The physicist Richard Feynman called the double-slit experiment the only mystery of quantum mechanics, and the data behind it is available in the published record going back to G.I. Taylor's 1909 single-photon interference work and Johnson's 1961 electron double-slit replication. Practical exercise 2. Search right now, in another tab, for Johnson 1961 double-slit electrons. You'll find the original paper or reliable summaries. Notice the interference bands in the published photographs. That pattern, and its disappearance under measurement, is the empirical core of everything we're discussing. Take 30 seconds. Go look. Come back. Now here is where the myth debunking matters most. You will encounter claims online that the observer effect proves human consciousness shapes physical reality, or that intention collapses the wave function. This is not supported by experimental evidence. Consciousness is not required. In delayed choice experiments, notably John Wheeler's 1978 thought experiment, physically realized by Jacques and colleagues in 2007, the choice of measurement can be made after the photon has already passed the slits, and the result is the same. Measurement determines particle-like or wave-like behavior, regardless of any human observer being present. The apparatus does the work. Decoherence, the leaking of quantum information into the environment through physical interaction, explains the transition from quantum to classical behavior without invoking mind at all. Speculative, some physicists, including proponents of relational quantum mechanics or QBism, argue that what counts as an observation may depend on the reference frame of any physical system, not just detectors built by humans. But this remains an open interpretive debate, not settled science. If you want to go deeper on quantum interpretations, Copenhagen, many worlds, pilot wave, we have a full explainer linked in the end screen right now. Watch it immediately after this one, because the interpretations change how you think about this result without changing the result itself. Back to your exercise. Look at the answer you wrote down. If you wrote yes, measuring changes a system, you were right, but probably for the wrong reason. Most people imagine a clumsy observer bumping into things. The quantum version is more radical. Even the most delicate possible measurement, in principle, still requires physical interaction, and that interaction is enough. There's no non-disturbing measurement at the quantum scale. This is not a limitation of our tools. It is a feature of the mathematical structure of quantum mechanics, encoded in the commutation relations between conjugate observables, position and momentum, for instance, formalized in Heisenberg's uncertainty principle in 1927. So what does this mean practically? It means quantum computing engineers must design qubits that stay isolated from their environment, shielded from stray photons, vibrations, magnetic noise, because any unintended interaction is an unintended measurement, and unintended measurement destroys the quantum coherence their algorithms depend on. The observer effect is not a philosophical curiosity. It is an engineering constraint costing billions of dollars to manage. Document this. Write in your notes. Observer effect equals physical interaction, not consciousness. That one sentence will protect you from a significant fraction of quantum mysticism circulating online. The evidence is in the interference pattern, and the interference pattern is in the data.